Okay, so we finally come to the last talk of this conference, and this will be by Marcello Barbosa Neto from the Federal University of Rio de Janeiro. And Marcello will tell us about defect engineering in superconductors and Fermi liquids.
Good afternoon, everyone. First of all, let me thank the organizers for the opportunity for me to give this talk here, and also for the wonderful staff of the IIP, who has welcomed me very warmly. So today I'm going to talk to you about defect-engineered superconductors and Fermi liquids. This is the work I've been doing. This is me, and I've been working with Mohamed Al-Masalami. We are both from the Physics Institute of Federal University in Rio de Janeiro. Mohamed was here until lunch, and then he bailed on me. I don't know why, but I'm the theorist, he's the experimentalist, and he has done a tremendous job in this work. So, what I'm going to talk to you about is the following. First of all, I'm going just to set grounds. I'm just going to review a few concepts about the resistivity of metals and alloys. I'm going to talk about non-magnetic impurities and Anderson's theorem. And then I'm going to introduce a type of defect that stabilizes Fermi liquid behavior in many systems. And then we're going to see how the enhancement and reduction of the critical temperature together with the Fermi liquid coefficient A can be related to the addition of disorder, of defects. And then we are going to understand how TC and A are correlated. I put emergence and correlation so that I could justify my presence here. And I'm going to finish with conclusions. Okay, you all know this very well, the resistivity of metals and alloys. We can pretty much generally say that the temperature dependence of the resistivity, there is some temperature dependence here. If the material becomes a superconductor, the resistivity drops below critical temperature. If you extend this line here, you get the so-called residual resistivity. And the exponent here of the temperature dependence depends on what kind of scattering mechanism we are considering. If we have, for example, for the residual resistivity, if we consider impurity scattering, there is no temperature dependence, and I'm talking about elastic scattering. Fermi's golden rule tells me that I should have some squared matrix element. This is a single electron problem, so I should have one time here the density of electronic states and the density of impurities. The same thing is valid for electron phonon scattering. At low temperature, we should get a fifth power here, otherwise the complete Bloch-Gruneisen function. Again, the square of the electron phonon matrix element. Again, it's a single electron problem, one time the density of states, and this should give me the inverse scattering time for electron phonon interactions. Then these are just three examples because I'm going to be interested in this one here. This is what gives us, according to Dow's theory of the Fermi liquid, this is what gives us the square temperature dependence. It's the electron-electron scattering. We have here a squared matrix element. But in principle, because this is a two-electron problem, one might expect here a higher power of the density of states. This doesn't happen because we know the initial and final states, they are not completely independent. They are kinematically constrained, and that's why we get the density of states here. And by the way, this also constrains the exponent here. At lower dimensions, for example, in 2 dimensions, you could expect T log T. In 1 dimension, linear in T. So the kinematic constraints also restricts the power of the temperature dependence. Okay, but if we add impurities, there is something that can happen. You add impurities, you raise the residual resistivity. If this raise of residual resistivity doesn't change Tc or the temperature dependence. We know that this is protected by Anderson's theorem, and we know that we are talking about this sort of impurities. So we're talking about substitutional disorder, interstitial, either external or self-interstitial, Frankel defect, vacancy. These are all point defects. And just to give you an example, take lead, then you bombard lead with germanium. You see that the residual resistivity goes up, but Tc is left unchanged. So this just tells us that indeed non-magnetic impurities, they produce no change in Tc. However, there are some defects that stabilize Fermi liquid behavior. You start with some temperature dependence, you add such defects, and you get a T squared. Not only that, if by adding such defects, the residual resistivity increases, you can also increase Tc and the curvature of the T squared term. You have a combined enhancement of Tc and A. This is, for example, if you get indium films and you bombard indium with indium itself, producing self-interstitials, for example. You see here, this is the Fermi liquid coefficient. It goes up with the residual resistivity as well as Tc. So delta rho is positive, Tc goes up, A goes up. We can have the other way around. We can introduce defects producing an increase of residual resistivity, but we reduce Tc and we reduce the curvature. So this is what happens, for example, if you have a vanadium-3 silicon, and again you do some irradiation process, the Fermi liquid coefficient goes down, Tc goes down. But again, this happens together, Tc going down, A going down. So what I want to study is what sort of defects are these that they stabilize the ubiquitous and robust Fermi liquid behavior, how Tc and A should be correlated with each other and with the residual resistivity, and how we can understand enhancement and reduction of Tc. So this is what we call the amorphization defect agglomerates. We are not producing isolated point defects. This is an example of a cluster or agglomerate or a complex, as you want to call it, of Frankel pairs that do not recombine. They are stabilized by some solute, by some anchor, but they are large defects. They can be created by irradiation or fast quenching from high temperatures to low temperatures, doping or co-deposition. And here you can see that besides breaking translational invariance, they produce important lattice distortion, and they soften the as this is something that I'm going to obtain here, but we can expect a softening of the vibrational spectrum. So the difference here is that normally, if you have point defects, you get a finite quasi-particle lifetime, breakdown of translational invariance, but according to Anderson's theorem, if we're talking about S-wave superconductors, nothing changes with Tc. These guys here, besides doing this, they, as I'm going to show, they modify the rules of momentum transfer at the electron-phonon coupling. So things happen at the level of the electron-phonon coupling. And they introduce uncertainty in the primitive unit vectors of the unit cell. This is an important ingredient we're going to use. So let's discuss first the clean case to make up my point, and then we go to the dirty case. If you look at Simon's book, this is the general expression for the electron-phonon interaction. These are the phonon polarization vectors. This is the momentum transfer. Normally, we have here the so-called electron-phonon structure factor, which has this expression here. But if you have a perfect lattice with one ion per unit cell, you can sum this up, you get a delta function, and you go back here, and you say that you substitute Q by K prime minus A, and you see that you can only couple the electrons to longitudinal phonons, and the momentum is conserved. If you want now, you can do what BCS did. You can do a second-order perturbation theory to obtain an effective electron-electron interaction. And this interaction is represented here. There is a single longitudinal mode participating in the interaction. The interaction can be written in terms of K1 prime minus K1, but there is explicit momentum conservation imposed here in the process. The momentum that is transferred to the phonon is absorbed by the second electron, and the momentum is conserved in the two steps of the process. This is a problem if you want to calculate the Fermi liquid coefficient A. And the problem is the following. You have to calculate using Fermi's golden rule, 2 pi over h bar, matrix element square, but there is a delta function here of momentum conservation. So you are in a tight spot. You can have three possible scattering channels that give you non-zero A. The so-called Baber mechanism, but for that you need two different Fermi surfaces with different effective masses. If you have a single Fermi surface, the other possibility is that it's large enough that you can go to the next zone and come back by umklapp scattering. If it's not large enough, if it's small, you have to have it multi-valued. You have to have a multi-sheet Fermi surface. This is a recent work by Dmitry Maslov. So either you have multiple Fermi surfaces or large ones or multi-valued ones, but the Fermi liquid behavior is observed in a plethora of systems with different types of Fermi surface, all sorts of topologies and sizes and feelings. And this is too specific to explain the robust Fermi liquid behavior. Now I can go to the dirty electron-phonon coupling. The same expression, but now I substitute the electron-phonon structure factor by a quantity in which I do a Gaussian average, so I do a disorder average on the primitive vectors of the unit cell. Because inside of this guy here, the primitive vectors are not very well defined, I make an average over disorder, and this control parameter here is essentially inverse to the delta, to the shift in the residual resistivity. So if this is 0, L is infinite, I have a perfect lattice. If this guy is increasing, the uncertainty is increasing, and I get a fuzzy lattice. The thing is, we can do this calculation exactly for an isotropic system, and we get this expression for the structure factor, which I plot here. For large L, we get just a delta function imposing momentum conservation. If you decrease L, you just get broaden and broaden, showing that you are relaxing the constraint of momentum conservation. With this expression, I can go back and calculate my effective electron-electron interaction. It does not conserve momentum anymore. I can transfer momentum inside these regions of that has some amorphousness in them. And because I don't conserve momentum, I can have contribution from all possible phonon wave vector, phonon modes, longitudinal and transverse. This solves my problem of the Fermi liquid coefficient. Now, when I do Fermi's golden rule, I have the matrix element square, no delta function here. I sum over absolutely all initial and all final states, and because of that, I get a square here in the density of states, together with the square here for the temperature, which now is valid for 3D system, thin films, and they are not kinematically constrained anymore. So this solves the problem of the robustness of the Fermi liquid. You simply integrate out all initial and all final states, and you get a robust and large and sizable A. If we want to discuss superconductivity, we have to calculate the framework we are using is Eliashberg's theory. So we calculate the Eliashberg spectral function. This is again the basic definition, but here we include the distorted electron-phonon structure factor. Again, because I have an analytic expression for this quantity here, I can also obtain analytic expression for the spectral function, and it's displayed here. If L is going to infinite, I do get something which is quadratic. just like in the Bi model. If L is going to 0, I get linear behavior. It's a well-known result by Bergman and Reiner since 73, that in amorphous superconductors, the density of states should go linearly with the frequency. So we see that as we introduce more and more of these amorphization defect agglomerates, L is decreasing. We have a shift of spectral weight from higher frequencies to low frequencies. So there is a softening, as I said in the beginning, of the phonon spectrum. This is again well known. I give you an example here. If you get tin, this dotted line is just the Eliashberg spectral function. For the crystalline case on the left and amorphous case on the right, you see that indeed you can use very well here. It's quadratic here at low frequencies, while here it's pretty much linear at low frequencies. So just saying that amorphization transfers spectral weight to low frequencies. We have an analytic expression, and for finite large but finite L, we can split the spectral function in a contribution which is omega square. It's a clean contribution, and amorphous contribution. So we have two scattering channels for the electrons. The electrons scatter for the in some regions of the sample in a pristine crystal, some regions where they've encountered these amorphization defect agglomerates, they scatter without momentum conservation. So what can we do now? We write down a BCS type Hamiltonian, and here in the effective electron-electron interaction, I just used the usual expression from Eliashberg's theory with the spectral function here, that we have an analytic expression. And in terms of some optimal frequency that is determined by the Fermi velocity and the superconducting coherence length. This is this optimal frequency is the frequency where the effective electron-electron interaction is maximal. So far, we could use analytic expressions, and everything was working so fine. But here, things got a bit complicated, so we replaced this spectral function by an Einstein spectrum, but with fixed area, but which is the total area under the Eliashberg's function. So this is the A here, but with respecting the fact that we have softening. So this Einstein frequency here should shift to lower frequencies. And this simplifies because you can integrate out and you get this. This is the curve for the effective electron-electron interaction. So the thing, now I can tell you what's going on. We have here the spectral function that I'm replacing by an Einstein frequency. By adding this order, I shift this frequency to lower, I shift this energy to lower frequencies. And what is going to happen to TC depends on what's the ratio between this Einstein frequency and the optimal frequency. If the Einstein frequency is too high, this is the case of weakly coupled superconductors. When I soften the spectrum, I go up. The effective electron-electron interaction increases, so TC increases. If the Einstein frequency in the pristine system, in the pure system, is already low, this is the case of strongly coupled superconductors, which are naturally overdamped. If I introduce this order and soften, I go down the effective interaction, and I reduce the transition temperature. So we did solve Eliashberg's equation, the linearized version, using the standard two-well approximation, double-well approximation, and we got TC, which has this typical Macmillan expression, where this lambda L is the density of states times the effective electron-electron interaction that I just presented. And so the behavior, as I change the residual resistivity, TC changes as follows. If we are talking about weakly coupled superconductors, it increases. If we are talking about strongly coupled superconductors, it decreases. And these are some examples that we have Mohammed had a tremendous job separating. You have zinc, gallium, aluminum, indium, gold, aluminum alloys, many systems. By the way, each of these disordered by different ways, quenching, irradiation, or any other. And they all exhibit this straight line behavior that starts to saturate here at the high disorder. While niobium, vanadium, 3 silicon, lead, and all other strongly coupled superconductor, they decrease with disorder. The decreases with disorder. Now I need to connect the transition temperature with A. And the thing is, remember that translational invariance has been broken. I do not conserve momentum. I have at my disposal all possible K states as initial states, all possible K states as final states. The inverse scattering times goes with the square of the density of states, square of the matrix element, and the temperature square. So I can put this guy here inside. And I remember that NEF times the interaction, including now the attractive and repulsive interactions, and renormalization of the density of states, this is the expression that I get for A. It's simply given in terms of lambda, mu star, the Coulomb pseudopotential, and the strong coupling renormalization factor. Again, with this expression and knowing that lambda is related to the effective electron-electron interaction, we see that in weakly coupled superconductors, the normal state of weakly coupled superconductors, A should increase, and the normal state of strongly coupled superconductors, A should decrease. And I give you here the example of indium, which was the first example that I showed you. A is increasing in a fashion very similar to the one we obtained. And again, vanadium 3 silicon, A is decreasing as we have obtained. So how to connect TC and A? Now it's a simple exercise. We have the expression for TC with inside the exponential 1 plus lambda divided by lambda minus mu. A is proportional to this quantity, the inverse, some proportionality factor here to give the proper dimensionality. And together, these two results impose this relation here. Tc divided by something with the dimensions of temperature should be equal to the exponential of something with the proper dimension divided by the square root of A. And to test this, we have plotted the log of Tc as a function of A to the 1 over square root of A. And you see that the scaling is very nice for the weakly coupled superconductor. It's pretty nice as well here. It deviates a little bit, but it works here for strongly coupled superconductors. These are just two examples, but I can show you what I'm saying, that this is a ubiquitous and robust behavior. It's because we were able to put Tc divided by theta and this exponential here for chalcogenides, pnictides, conventional BCS, weak coupling and strong coupling, including MgB2, and here the example I showed you, vanadium 3 silicon, also heavy fermions. You see that these are large energy, medium energy, and small energy corresponding to larger Tc, intermediate Tc, and low Tc. But they all fit in this universal curve here, and they can all be scaled into this universal curve. So to conclude, if we are talking about non-magnetic point defects, isolated point defects, we can introduce these guys, and Tc should not change, A doesn't change, or the other temperature dependence of the resistivity, it doesn't change. And this is guaranteed by Anderson's theorem. The moment I start to introduce disorder that can be classified as these agglomerates, that we call the amorphization defect agglomerates, These importantly distort the lattice, lift all the kinematic constraints, breaking momentum conservation at the electron-phonon coupling, soften the phonon spectrum, and if you put all this together using Eliashberg's theory for superconductivity and Boltzmann transport theory for the resistivity, we end up with this formula here, in which the only control parameter associated with disorder is this uncertainty parameter in the definition of the primitive vectors of the unit cell. So, thank you very much for your attention.
Questions?